SwayamPrabha. Digital India. Educated India.
Good morning, friends. When I am talking today, we are all saddened, sudden demise of Dr. Abdul Kalam. And he had been a real source of inspiration for all of us. We used to have very close interaction with him. Recently also he was here. I'm sure that this is the right occasion that whole of this course we dedicate it to Dr. Abdul Kalam. And make sure that whatever dreams he had also become your dream. And that is the best way to pay homage to Dr. Abdul Kalam. I'm sure he will be around and watching all of us, how sincerely we are working hard to take our country to the esteem high. Coming back to our effort to understand airplane performance, and as we agreed that we'll build this course in a manner that at the end of the course we should get some idea how to design an aircraft, because we may offer another course on stability and control, purely on stability and control, and third course on aircraft design, subject to the response I get from all of you. If you really think it's helping you, we are here to help you out. If you think books are sufficient, fair enough, no issues. So let me try to recapitulate what we were doing from the perspective of designing an aircraft. When you want to design an aircraft, you know that there are phases. Typically I can draw it like this. Here it is the takeoff and taxiing. In fact, it starts taxiing, then goes, attain a particular speed, then put the front wheel up, then climb. So this is the climb phase, and this is, the cruise. Then this is loiter and landing. Okay, this all we now know. What are the primary characteristics for these phases, and how do I relate it to aerodynamic parameters, geometric parameters, inertia parameters of an airplane, to see that really pilot can achieve all those things. That is, design has that bandwidth where pilot can extract depending upon the requirement. Now, since we are focusing on design aspects, we also discuss something on stability, CM and CL. And remember, we talked about trim point, and that is the point which is the trim point. I can trim the airplane at the CL, meaning thereby I can fly at this CL with lift equal to weight, and there are no unbalanced moment. So moment is zero, that is why CM is zero at this point, and the CL is typically if I am concentrating on cruise, then CL corresponds to lift equal to weight, and CL is 2W by S by rho V square. That is CL. So now if I see this point, and if I decide, depending upon my requirement, if I decide, I will ensure that the CL is such, I have decided, so that if I slightly change the CL, there should not be large increase in the drag, because because of CL there is an induced drag also, and because of CL, even if there is no induced drag for aerofoil, still CD will increase with CL because of flow separation. When I talk about CL, a wise designer ensures that he appropriately picks up the CL somewhere here mid value of a drag bucket, so that even if there is a change in CL, there is no large change in the drag coefficient. Okay. Also, we know by now that mostly this transport airplane, they are designed for a static margin could be between 5 to 10% or 5 to 15%. So I know also that DCM by DCL is nothing but minus static margin. So static margin is 15%, let's say, 15%. The slope will be, if static margin is 15%, then the slope DCM by DCL is minus 0.15, because I know DCM by DCL is minus static margin, non-dimensionalized with the mean aerodynamic chord, right? So once I know 15% is my static margin, that I know the slope, I know what CL I'm going to fly. Let's say this CL is 0.6. I'm going to fly. Then I know how much Cm naught the airplane should generate. Well and good if it can automatically generate without deflecting elevator. And that also we know this is possible by giving tail setting angle and also locating the wing so that AC of the wing is ahead of CG of the airplane. All these things we have done. I will be now highlighting few small things which are very relevant for designing an aircraft. Very preliminary, but yes, if you understand this, when you do design course, you will be ready for it. Let us see first Vstall. What was Vstall? Vstall was 2W by S rho CL max. You are all now expert. What was the interpretation of Vstall? That this is the minimum speed with which the aircraft can maintain lift equal to weight at a given altitude. And what was CL max? This is the maximum CL I can get from the airplane at a particular angle of attack. So this angle of attack is alpha stall, and this point is CL max. You all know this. As a designer, what do you want? The Vstall should be high or low? Remember, if Vstall is high, that means you need larger takeoff distance, because you know V takeoff is proportional to Vstall. It is 10 to 30% or 15% of within that range of Vstall. So Vstall is high, V takeoff will be high. So there are two possibilities. I have to put a bigger engine so that it can accelerate to that speed within shorter takeoff distance, or if I am not able to increase the engine power, then I will need larger takeoff distance. So who plays a vital role for a given altitude and given aerofoil? It is the W by S, and W by S is called wing loading. You could see from here, if W by S is large, Vstall also will become large. What is the meaning of W by S large? Means relatively the S is small. That is why W by S has gone high. Or in other way, if I say, if I want to reduce Vstall, keeping other thing constant, I must have very low value of W by S. Low value of W by S means what? S is relatively high, and which is correct. If S is high, you get larger lift, so you will be able to take off earlier. But there is a problem. If I increase S to a large size, the drag also will increase. The moment drag increases, the engine power required to maintain the drag also increases, so that again increases the weight. So this W by S goes on an iteration cycle. So one thing we should understand, the wing loading is very important. So I have to select wing loading from takeoff from takeoff distance point of view. So we understand here I have to select W by S, keeping in mind takeoff distance required. We always try to ensure that takeoff distance is as low as possible. This is one. Now, second part you see. If I come to cruise, what do you see in cruise? Lift equal to weight, or half rho v square SCL equal to weight, or W by S equal to half rho v square CL. This is one expression we get. Okay? Also, please understand, since thrust equal to drag and lift equal to weight, I know thrust equal to W by L by D equal to W by CL by CD. Okay? What these two relationships telling us? This is telling that if we have decided what will be the CL cruise, and for a given altitude, I should have this much of W by S to maintain lift equal to weight. Please understand, if we have a priori decided what is the altitude you are going to be flying most of the time, let's say for a jet engine, you will prefer to fly at around 11 kilometers, okay? Where engines are efficient, relatively more efficient. And suppose you have decided what is the cruise speed. Then since CL design is also decided from other criteria, so this also tells you how much wing loading you require to maintain lift equal to weight. So this is also W by S from cruise. The story doesn't end here. You know that if I want to fly at a CL where thrust required is minimum, then I have to fly at a condition CL by CD is maximum. You are all expert now. This means I have to fly at CL equal to under root CD naught by K. Okay? So now this expression becomes W by S. I can now write half rho V square to CD naught by K. So this is another requirement, that aircraft must have this much of wing loading so that it can manage lift equal to weight, as well as it will fly at a thrust required minimum. You could see that I can manipulate W by S for given rho and V by altering the value of CD naught and K. What is K? K is 1 by pi aspect ratio E. So I have a flexibility in altering the value of aspect ratio, and also CD naught. I can make the aircraft smoother. I can reduce the skin friction. So depending upon the requirement, again, I find there is a restriction on W by S because of cruise. Okay, let us see what happens during climb. Check for climb. This is drag, this is lift. So I know T minus D minus W sine gamma equal to 0 for a steady climb. Okay? So what I am seeing here, I am seeing T by W minus D by W is equal to sine gamma. Or T by W is equal to sine gamma plus D by W. So if I am really going for a climb, please understand as a designer, when I am climbing, the thrust has a duty to lift the weight, carry the weight with it, right? That is why T by W becomes another important parameter. And here you could see, if I want to climb at a particular angle gamma, then T by W, I can get an initial estimate by just taking the sign of that value, because D by W, if I approximate it as D by L, because W equal to L, W, although during climb W is not equal to L, W cos gamma equal to L, you know, but for gamma small, I can replace W by L, so I get an expression T by W is equal to sine gamma plus D by W, and if I assume L is roughly equal to weight, during climb, please understand, lift is not equal to weight, lift is actually equal to W cos gamma. Since gamma is small, I am taking this approximation. As a designer, I always do that. If I do this, then I get T by W is equal to sine gamma plus D by L, or this is equal to sine gamma plus 1 by L by D. This is during climb. So what was T by W during cruise? If I try to find out how much thrust is required during cruise, so I can always get that expression by put gamma equal to 0 in that expression. So I'll get, using the same expression, T by W equal to 1 by L by D, which is equal to 1 by CL by CD, which you are not surprised. You know that this is already have derived many times. We are trying to estimate the value of T by W for cruise. This is for cruise, and this was for climb. See here. Okay. Typically T by W should be how much for a cruise airplane? You could see that for a cruise what I require, T by W should be, let's say CL by CD I am flying at 15, is a good number most of the time. So it will be 1 by 15. We are looking for a rough estimate of T by W during cruise. If I say L by D or CL by CD is 15, which is a realistic number, then T by W will be around roughly 0.07. Okay? Suppose you are flying at a CL by CD of 10, then T by W will be 1 by 10, and that is 0.1. This is the requirement in the cruise. You could see that these values are pretty less. And you will appreciate it more if I come back to T by W of climb. Okay, requirement of T by W during climb. Let us see how much it happens to be. We have seen T by W I can write as sine gamma plus 1 by CL by CD. Let's say I am climbing at 30 degree. So T by W equal to sine 30 plus 1 by, let's say CL by CD is 10. This is CL by CD is 10. Then how much it is? This T by W is coming to 0.5 plus 0.1, 0.6. Do you see the difference? For taking the mass through a climb phase, the T by W requirement will be predominant. You will not decide T by W from the requirement of cruise. We will decide the requirement of T by W from the requirement of a climb. Okay? So you could see that if I change gamma to a lesser value, the T by W requirement will be less. So depending upon what gamma you are flying, the T by W will be the deciding factor, right? And remember, this we are assuming that it is going and climbing at a steady speed, no acceleration, right? So this will give you an idea about how to select T by W for your airplane depending upon requirement. Suppose you are designing an airplane which you want, it should just go vertically like this, then definitely you understand that T by W should be more than 1, right? Am I correct? Suppose if I am flying like this, I want climbing like this, 90 degree, then naturally T and W, T by W should be greater than 1. A huge engine is required. Huge power, thrust is required. So there are two important parameters. One you have seen, the wing loading, W by S, and T by W thrust loading are extremely important parameter to design an aircraft. And you have a fairly idea how to get an initial estimate of wing loading. You can find out the wing loading also by taking into account what is the Vmax, maximum speed required, what is sort of an acceleration you want, because you know as I increase S, although lift increases, drag also increases. That means if you want to really do a high acceleration, the large aspect ratio wing are not in demand because that will have a lot of drag and a lot of power has to be dissipated. So that is why for a high-speed airplane you will find the aspect ratios are small. Okay, is it clear now? Okay. If I have understood about T by W and W by S, and while discussing I am talking about high speed, let us also have few glimpses, few understanding of what is a high-speed airplane and how wing platforms are configured. When I say high speed, we are meaning thereby in today's context Mach number greater than 0.3 or typically 0.7, 0.8 or supersonic could be, depending upon type of airplane, you can go up to 2, 2.5. The moment you are increasing the speed of the airplane, you will find there is a change in the configuration of the airplane. For example, for a low speed, you will find mostly it is rectangular. People tried elliptical also, right? But base is rectangular. You will find for a low speed also some sort of a tapering is done like this. Tapering means if this is tip chord and if this is root chord, the Ct by Cr is less than 1, and typically this value we will find around 0.4 to 0.5. Low speed you will find the airplane is given that much of taper ratio, and that helps in bringing the wing platform closer to a elliptic wing type. You know, not exactly, but yes, it helps. Also, you see that, very important, please understand this. One of the major challenge for flying is the natural tendency to fly at a higher angle of attack, if possible, at a lower speed. So that engine power requirement is less, and you get a lot of lift from the interaction with the medium. As we try to fly at higher angle of attack, I have a danger. I should not cross alpha stall. Also, we understand, suppose I am flying here, although I am not in alpha stall, but because of some upward gust, local angle of attack may change and the airplane may go into a stall. Suppose the airplane has gone into a stall, and you know this is the elevator. What will happen? If the airplane goes into a stall, then the elevator will not have that much of sensitivity. Its effectiveness will reduce. So if the airplane goes into a roll or a yaw or combination of that, spin, the elevator will not be effective enough to bring it back. So what is the wise way of handling it? What we do is we ensure that if at all stalls a region we are approaching accidentally, then let the root portion stall first, then let the tip portion stalls. So that the moment there is a stall in the root, there will be a warning to the pilot, and that time aileron is not installed, so it will be effective, it will take care of the adversaries. But how do I do that? If everything is similar here, then naturally all the parts will stall almost equal at the same time. So what is done is some geometric twist is given to the aerofoil at the tip around this region. That is, there is a deliberately negative angle is set on the aerofoils which are near the tip. So that even if there's a 12 degree or 13 degree stall angle, this portion will see less than 12, 13 degrees. So the root will stall, but this gentleman will not stall. This is one way, which is called geometric twist. Another way possible, you put different aerofoil. You put aerofoil here and here, because this is completely, the contour is controlled by the aerofoil shape. What do? We do not give geometric twist, but we put aerofoil here, which has a characteristic of stalling earlier than the aerofoil here. That I can easily decide by selecting the aerofoil through their nose radius or T by C, etc., etc. For example, if T by C is higher, it will likely to stall earlier than aerofoil where T by C is smaller, right? Same thing will be true for nose radius. I can design that. So what is the second step? I put aerofoil here near the root, which has the characteristic of stalling at a angle, let's say 13 degrees, and we select aerofoil here, which has the characteristic of stalling at, let's say, 14 degrees. So the moment it stalls at 13, this man has not stalled. So this effectiveness is available, and you can do correction. So this is one aspect. Thank you very much.